Hello everyone, myself Pulakesh Chetia, Assistant Professor, Faculty of Engineering and Technology of Assam Downtown University is going to give a lecture on stress-strain curve. Okay, so now what is a stress-strain curve? Okay, a stress-strain curve for a material gives the relation between stress and strain. These curves generally reveal many of the properties of a material. Okay, so here are the following information that can be obtained from a tension test. So number 1 is proportionality limit, number 2 elastic limit, number 3 modulus of elasticity, number 4 yield strength, number 5 ultimate tensile strength, number 6 modulus of resilience, number 7 modulus of toughness, number 8 percentage elongation, number 9 percentage reduction in area. So let's move on to stress-strain diagram of ductile materials. Ductile materials, say for example mild steel. Okay, so let me explain this diagram to you. So this is a stress-strain curve. Okay, so on x-axis we have strain and on y-axis it's stress, and this is the point of origin. Okay, so it is observed from the diagram that stress-strain relationship is linear from the point O to point P. This one is linear. OP is a straight line, and after the point P the curve begins to deviate from the straight line, as you can see in the diagram. So Hooke's law will be applicable here. And what is Hooke's law? Okay, Hooke's law states that stress is directly proportional to strain. Therefore, Hooke's law will be applicable only to up to the point P. So the term proportionality limit will come here. Okay, so what is proportionality limit? The term proportionality limit is defined as the stress at which the stress-strain curve begins to deviate from the straight line. Here in this diagram, after point P the curve begins to deviate, and so point P indicates the proportional limit. Okay, next we find this modulus of elasticity. Okay, the modulus of elasticity, or Young's modulus, is the ratio of stress to strain up to the point P, this point. Okay, it is given by the slope of the line OP, this, and therefore E will be equal to, this is angle theta, so tan theta will be Px by Ox, and this will be the stress by strain. Px is stress and Ox is strain. Okay, next, if specimen is stressed beyond point P and up to point E, this point, okay, it will regain its initial size and shape when the load is removed. This indicates that the material is in elastic states up to point E. Therefore, this point E is called elastic limit. Okay, this point E. Next, when the specimen is stressed beyond point E, plastic deformation occurs and the material starts yielding. During this stage, it is not possible to recover the initial size and shape of the specimen on the removal of load. It is seen from the diagram that beyond point E, the strain increases at a faster rate up to point Y1. This point Y1 is called upper yield point. In case of mild steel, it is observed that there is a small reduction in load and the curve drops down to point Y2, which is lower yield point, immediately after yielding starts. The points Y1 and Y2 are called, as I have already mentioned, upper yield point and lower yield point respectively. Next, after the yield point Y2, plastic deformation of the specimen increases. The material becomes stronger due to strain hardening, and higher load is required to deform the material. For ductile materials, the dia of the specimen begins to decrease rapidly beyond the maximum load point U. There is a localized reduction in the cross-section area called necking. As the test progresses, the cross-sectional area at the neck decreases rapidly and fracture takes place at the narrowest cross-section of the neck. This fracture is shown by the point F on the diagram. The stress at the time of fracture is called breaking strength. Okay, so let's go to give the definition of proportional limit. As I have already mentioned, the term proportional limit is defined as the stress at which the stress strain curve begins to deviate from the straight line. Point P indicates the proportional limit. Next, modulus of elasticity. This is also I have explained. Number 3 is elastic limit. The elastic limit of the material is defined as the maximum stress without any permanent deformation. Okay. Number 4, yield strength. The yield strength is defined as the maximum stress at which a marked increase in elongation occurs without increase in the load. Number 5, ultimate tensile strength. The stress corresponding to the point U is called the ultimate strength. The ultimate tensile strength is the maximum stress that can be reached in a tension test. So next, we move on to stress strain curve for brittle materials. Brittle materials can, for example, cast iron. So in this figure we have seen the stress strain diagram of brittle material, that is cast iron. So let me explain this curve. Okay, it is observed that such materials like cast iron do not exhibit the yield point. The deviation of the stress strain curve from straight line begins very early, and fracture occurs suddenly at the point U with very small plastic deformation and without necking also. Therefore, ultimate tensile strength is considered as failure criteria in brittle materials. Okay, so I have written here that it is observed that such materials do not exhibit the yield point. The deviation of the stress strain curve from the straight line begins very early, as I have already explained this to you, so you can go through it. Okay, next, percentage elongation. The percentage elongation is defined as the ratio of the increase in the length of the gauze section of the specimen to original gauze length, expressed in percent. So percentage elongation formula will be equal to L minus L0 divided by L0 whole into 100. Number 7 will be percentage reduction in area. Percentage reduction in area is defined as the ratio of decrease in cross-sectional area of the specimen after fracture to the original cross-sectional area, expressed in percent again. So percentage reduction in area, the formula will be A0 minus A divided by A0 into 100, where A0 equal to original cross-sectional area of the test specimen and A equal to final cross-sectional area after fracture. So let's solve one problem regarding stress strain curve. Okay, so here is the question. The following data were recorded during tensile test made on a standard tensile test specimen. Original dia and gauze length is given as 15 mm and 60 mm. Minimum dia at fracture is 10 mm. Distance between gauze points at fracture is 75 mm. Load at yield point and at fracture equal to 40 kN and 45 kN. Minimum load specimen could take equal to 70 kN. Make calculation for number A, yield strength, ultimate tensile strength and breaking strength. Number B, percentage elongation and percentage reduction in area after fracture, and number C, nominal and true stress at fracture. So here comes the solution for the problem. First we need to find out the original area, that is A0, which is equal to pi by 4 15 square, which will be equal to 176.625 mm square. Next we have to find out the final area, that is AF, which will be equal to pi by 4 into 10 whole square, is equal to 78.5 mm square. Okay, so for point A we need to find out yield strength, which is equal to 40 into 10 to the power 3 divided by original area, that is 176.625, which is equal to 226.47 Newton per mm square. Next we have to find out ultimate tensile strength, which is equal to 70 into 10 to the power 3 divided by original area, that is 176.625, which comes out to be 396.32 Newton per mm square. Breaking strength, which is equal to 45 into 10 to the power 3 divided by original area, that is 176.625 again, so it comes out to be 254.78 Newton per mm square. Next, number B. Number B, we need to find out the percentage elongation, which is equal to LF minus L naught divided by L naught, which is equal to 75 minus 60 divided by 60 into 100, so it comes out to be 25%. Okay. Next, percentage reduction in area, the formula is A naught minus AF divided by A naught, which is equal to 176.625 minus 78.5 divided by 176.625 into 100, which comes out to be 55.56%. Next, number C, we need to find out the nominal stress or breaking strength. So it is equal to load at fracture divided by original area. So load at fracture is given as 45 into 10 to the power 3, and original area we have found out as 176.625. From after calculation we received as 254.78 Newton per mm square. Next, we need to find the true stress, which is equal to load at fracture divided by final area. So load at fracture is same, 45 into 10 to the power 3, and final area we have calculated earlier as 78.5, so it comes out to be 573.25 Newton per mm square. So we have calculated all the values that we needed according to the question. So with this I have come to the end of lecture on stress strain curve. Thank you everyone.